Today on Zero to Lit On, I have in for a complete rebuild, an absolute mammoth of a laser. And when I say mammoth, I mean it's old and it's huge. In fact, it's 2 feet this way, 2 feet this way, and 1 foot deep, giving me roughly an internal volume of 4 cubic feet to work with. I'm going to be making this laser about 65 watts, so we're going to use a lot of that internal volume as efficiently as we possibly can. So, you want to see what's inside of it? Sure you do. Let's go ahead and take the top off. Now, mind you, I have taken some parts off already, just for measurement purposes and so on and so forth, but get a good idea of what's inside. Flying camera action away. Now, when this laser was originally built, it had a 5-watt GPSS 532 nanometer laser and a 10-watt old school Cavant 10-watt laser. In fact, the same one that I rebuilt on my YouTube channel. Those lasers have been removed, and the only laser head that is in here right now is the replacement 15-watt, 15 or 20. It's a bright green 520 nanometers direct diode, so that's one of the lasers that's going to go in here. The other two lasers is a 32-watt dual blue, which uses 445 nanometers and 465 nanometers, giving us a nice, crisp, true royal blue color. And then a 20-watt 638 nanometer red laser. And the order that they're going to sit in is red, blue, green. Let's take a look and see what's in here already. Let's go to the back section over here. We have a couple of potentiometers. Those are for the color channels. We go ahead and make sure that those are operational. If they're not, take them out and replace them. Over here we have the key switch for activating the laser, and then the input for the remote emergency shut-off button. We're of course going to have to add some things in here as well. We're going to have to add in some remote interlocks, some interlocks for the case so it shuts off when you take the cover off, and then a 30-second delay, because those are all required in order for a laser to be FDA and CDRH certified. Let's see what else we have in here. We have the laser driver for the 20-watt 532 nanometer green, and then we have the power supply that runs that laser and laser driver here. We got this mysterious power supply here that'll be taken out. We have these two power supplies here. Those are 24-volt power supplies that are all wired in series to give the positive and negative 24-volt rails to drive the galvanometers. Now, currently installed in this laser, there are iMagics, so EMS 4000s, and we're going to pull those out and put in some Dragon Tiger galvos. I think they're Dragon Tiger. But the reason we're going to do that is not because the EMS are bad. They're actually pretty good galvos. The problem is that the mirrors and the handling of those mirrors, the mirrors are too small, and I don't think these will handle bigger mirrors. So that's why we got the other galvos. They're much bigger mirrors, but double the size. So I want to say those are 6 by 12-ish mirrors, millimeters, and we got in some mirrors that are 18 by 12, so much bigger. Unfortunately, it's either going to be slower or a more narrow scan angle, but when you're working with a laser beam that is that powerful, it's also wide, so a little bit of a kpps loss on that, but that's what we have to work with. So here's my thinking, and here's what I'm going to do. We have 1 inch underneath the optical breadboard here that we're going to work with. Our heat sinks are going to be underneath the laser heads. We're going to have red, blue, green, and we're going to have the kinematic mounts here. We're going to have the galvos here. This is all going to be taken out. In fact, I'm going to take the whole laser apart and just gain access to the optical breadboard itself. I'm going to mount a lot of the laser power supplies up in this area, directly behind the laser. And behind here, I'm going to have, I think, 6 or 7 80mm fans. They're 48 watts apiece. That's going to be a lot of fan power. And the reason why we need that much is because we're not only removing the heat, about 60 or so, 60, 80 watts from the laser diodes themselves as far as heat management or heat production, but we have all the thermoelectric coolers on the inside too that are for the stabilization of the temperature for the optical decks on the inside of the laser head. So we have to dissipate a couple hundred watts of heat out of the laser. That's a lot of heat to get rid of in this kind of area. So we're going to manage that as best as we can. I've got all the heat sinks that are going to go underneath. There will be 4 underneath the red laser, 3 underneath the green, and 3 underneath the blue, and maybe a heat sink underneath the galvanometers. But yeah, so it's going to be a lot of work. The first thing is to pull everything out, pretty much. I'm going to pack up the EMS 4000s, make sure those are nice and safe, along with the power supplies and stuff like that. Package that up until it's ready for placing in the optical breadboard, marking out. I am not going to use the screws that go into the optical breadboard. I'm actually going to fill these up with insert screws because I want the maximum amount of heat dissipation between the lasers and the heat sinks underneath, and I don't want dust coming up from these holes. So I want to make this as dust proof as possible, because it's important. If you get dust on the optics, that laser power will just hit the optics, hit the dust, burn in on the optical coatings, and trash them in no time flat. So that's important. Dust management is definitely important. So yeah, big project. Anyway, I'm going to put the camera back and I am going to start taking apart this laser. At this point, I have the entire laser taken apart, and I have the optical breadboard of which to work on. And I'm going to treat this like my magical laser pizza crust and put some toppings on it. Now, just like with all pizzas, opinions and topping selections may vary, but let me go through with what I've chosen and talk a little bit about why I chose those parts. So I'm going to work mostly from the back and this way with my part selection, and I'm going to start with the fans. So even though it's about 65 watts of optical output because of the efficiency of the lasers and other components like the TECs and so on running inside of the laser, it's going to be a couple hundred watts of thermal energy that we need to get out of the laser. So that's going to require a pretty hefty cooling solution. So I have a bunch of fans, and the fans that I chose are these Delta PFR 081 2XHE fans. And these are pretty good server fans, and you get them pretty cheap online right now. An excellent solution for the price. I'm actually pretty impressed with these. They don't have RGB LEDs inside of them, but hey, performance. So we're going to put a couple of these in the back of the laser, blowing downwards, and onto heat sinks that are going to be mounted on the bottom of the optical deck. So I'm going to put this aside for now, and I'm going to put the fans representing what we will install in the case. So they have to be 1 inch this way to make room for the frame that goes around the bottom. So that's about 1 inch. So 6 of those, I think, is what I'm going to put on. Grab fans. Right there. Yeah, probably 5 looking at it. So each one of the fans requires a hole that should be about 70 millimeters in diameter for the air to blow through and under. So that's going to be one of the first things that I do, is mark out that circle and do all those holes, as well as tapping with the screws. So air is going to come down this way, out through the bottom like this, and through the case. So that's our cooling solution. Now the next thing to put on is the laser heads. So I'm going to start with the power supply for the red laser. Let's go ahead and find that. Alright, so the power supply for the red laser is going to sit probably over here. And we're going to put the drivers over here for the time being. And then right next to that, I am going to install the red laser head itself. So that'll sit right here. Let me go grab that. That is a 20-watt red laser. And that'll sit in the laser about right there. And snug it up along the side, about like that. That'll give us a little bit of room in this area too for the galvanometer power supply. I'm probably gonna bring this back a little bit for that. All right, then the next thing to put on there is the blue laser. Grab that. So this is a 30-watt blue laser. That's gonna sit right here next to the red, probably spaced out a little bit like this. And then we're gonna have the green laser head over here in this section. And this is a 15-watt green. So that's gonna sit there like that. And there needs to be a little bit of room because there are fans installed on the one side over in this area. So yeah, green, blue, and red, totaling 65 watts, 15, 30, and 20. On the bottom of the actual optical breadboard, as I said, there's going to be some heat sinks under each laser. So the heat sinks that I'm going to use are, if I remember right, 300 millimeters this way, maybe 600. Yeah, 600 by 25 by 150. And I'm going to use 4 of these. So keep in mind they're going to be underneath the lasers on the opposite side of this, but I'm going to put them on top just for spatial representation. So there's all the heat sinks for that. Like that. Grab the rest of them. So 4 for the red. And 3 each for the green and blue. So like that. And like that. So on the bottom of the laser, the air from the fans is going to come in from the back, going to get blown down under the optical breadboard across these heat sinks, and that's going to vent out on the bottom. We're going to put feet on the bottom of the laser, raise it up about 1.5 inches, and that should provide good airflow. In fact, with those fans, once the laser's on, it should weigh about 10 pounds less because those fans are pretty beastie. A couple of other things to put in, which are the drivers for the green and the blue laser. So go ahead and put those in place. So the driver for the green, we can sit over in this area, and I'm going to have them facing so the airflow is facing that way. I don't want any dust falling on the optical table, so I don't want them like this and bringing airflow this way. So that's gonna sit like that, right on top of probably a metal platform that's gonna go over the laser heads, and it's gonna be on probably 8 to 12 standoffs that are gonna go right in the optical table. Gonna be above the lasers, maybe about 1 inch, and provide airflow and cooling, which these drivers are gonna sit on. So that's gonna be right above this laser, and then got the power supply for the blue. So that power supply is probably going to sit right in the back here, just like that. Some wire management is going to happen. Probably those more forward like this. Those over here like that. That's good. Yes. Okay. Awesome. The blue driver is going to be situated just like that on top of that same plate. And the plate's going to extend this way. And then we have our two red drivers that'll sit there just like that. And then all the cables from the laser heads themselves are decently long, so they're all going to plug in pretty easily. So it should look like a really clean build on here. Yeah, that'll plug in, no problem. These are backwards. So yeah, that right there is the general game plan. And of course, with the fans taken out of these metal cages, I'm going to put in probably a metal here up and over and give that a nice ductive curve on the inside too. But yeah, right now that's kind of where I'm going to go with this project. So this is the first thing to really take care of is making the holes for the fans. So 7mm wide holes and marking out the screws where the screws need to go and tapping that. So and then I'll go marking out the laser heads, other power supplies and stuff like that. But mark out this, mark out these, and the laser heads, tap those, move on to the heat sink, and so on and so forth until this is a complete laser. But there's a lot of work ahead of me to build this. Silly me, I just forgot. There's also optics and galvos. So let's take a look at the optics. I have kinematic mounts here. They don't have the right optic on them, but we'll have one kinematic mount like this, another like this, and another like this. I might even flip them around like that, quite honestly, so that they're easier for the user to adjust. I think that'll also work if I can get away with it. So yeah, have that like that. And of course the galvanometers, they're going to need to be in here too. One thing to note is that these lasers are actually lower as far as the output level on the front of the laser head than this one. This is actually elevated by about 5mm, and of course all those beams need to line up. So there will be another optical mount here, which will take the output from the red here, reflect it this way, and then forward. So that'll drop the beam down in height to match the height off the optical deck as the other lasers. Now let's take a look at the galvanometer. As I said earlier in the video, the galvanometer is a set of Dragon Tigers. These are DT30 Pros. They have quite a large mirror on them. Those need to be cleaned. But yeah, so the galvos will actually sit here behind the output of the red laser, and they'll be raised up on an aluminum block to give it the appropriate height to go and correspond with the height of the lasers coming out of the laser modules. But yeah, so that's the full plan. But as I said, the first thing is fan holes. Can't do anything cool if we can't cool anything. At this point, I had the fans pretty much placed on the optical breadboard where I want to mount them, and there's a couple of things I need to do. So the first thing is I need to mark out the 4 corners on each fan where I'm going to tap and drill for the screws that'll hold the fan on the optical breadboard. And I also need to cut the 70 or so millimeter wide hole in the breadboard that'll allow the air to flow through and into the heat sinks on the bottom of the optical breadboard. So luckily I come from a whole species of tool builders, and I built some tools which will help me do that. So I built this jig out of 5 of the little fan blade finger covers that go over these fans. We're not going to really use these anyway. And then I also built this, which will let me do the circle for the fans. So I'm going to go ahead and move these out of the way. And now I also want to find an area which will give me a little bit of building room for the shroud that'll go over the fans and for the air ducting. So let's see. I want some space on this side. Yeah, that gives me about an inch there and about an inch and a half there. Let's move this over just a little bit. And then lastly, I want to make sure that I don't land in an area with one of these holes where there would be a hole already drilled in the optical breadboard. So I'm gonna have to find a sweet spot for these holes to go. So I think I'm gonna have to move this out towards this way a little bit. How much? Not that far. That's pretty good, actually. I'll take it. So I'm gonna find a spacer that'll go in here, and then we'll have that pressed against the spacer, have that all lined up. Not exactly what I thought I'd use, but it'll work. All right, and line that all up. Good, 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 good. Okay, press that against the this side. Looks clear. All right, I'm gonna mark those out real quick. Excellent. And then the circles. Yeah, just like that. That'll work real well. Alrighty, it's drilling time. Let's try not to injure myself. Alright, so I am going to actually go and get some tape. I'm going to put tape on the bottom of my reciprocating jigsaw because I do not want the table that it rests on to scuff up the optical breadboard here. So give me a moment. Grab that. Always something else to grab. Now before I get into sawing, I want to show you what I did to my reciprocating jigsaw. As you can see, I put tape on the bottom so that way it doesn't scuff up the coating on this optical breadboard. Other than that, we're good to go. So I'm going to try to cut circles, and not exactly what humans are best at doing, but I am going to do what I can, and then we'll go ahead with sandpaper and some other stuff, make sure that those look all really nice. But right now, rough circles, that's the goal. So let's go ahead and do that. I'd love to use a lubricant, except that would take off all my markings. So, you know, there is that. So what have we learned? Well, we learned that sawing through aluminum that's this quality and this thick definitely requires lubrication. Anyway, we have a hole over here that's pretty much nice and sanded and taken care of. We got this rough hole that has been cut out here. And I am going to clean up this hole. First thing I'm going to use is a coarse file. So this will get off a bulk of the material that's still on there. So for example, these edges right here and so on. A file is one of the best things you can have for doing any kind of metal work. Lasts a while. Definitely better than sandpaper for this particular task. So I'm going to go ahead and knock off some of those rough edges. Alright, now with most of the rough edges taken care of, we can move on to a sanding drum on a rotary tool. So we'll go ahead and prepare that. Use the Dremel here at a low speed, because unfortunately the easy lock mechanism is a complete joke. So, you know, safety first. Seriously, not a good look, Dremel. Not a good look. That looks fairly good. Air can go through that. Yeah, and the other holes are, for the most part, already done, so they look good. Yes, air can blow through all of those. At this point, I am going to drill out the corners where I center punched earlier, and then I'll go through and I'll tap each one of those 4 corners for the screws. I think I'm going to use 632 screws on here. It's going to be a project that has a bunch of standard American size and then a whole metric size. I prefer metric because I'm used to a base 10 system for reasons. 2 of them, actually. But yeah, so I'm going to go ahead and do that. Now, despite the gossip around the water cooler and the internet memes discussing how tapping threads into metal can be difficult, it's actually a pretty rewarding skill to develop. So I'm going to be doing that. I've got my manual hand tap here, my 632 tap all loaded in, ready to go. Now, there's some things that'll help when you're doing your own threads. Firstly, the right appropriate drill bit in order to match up with the tap. Very important. In some cases, you can actually go and buy kits that have the right drill bit already with the tap good to go. The second thing that'll help immensely is lubrication. So I'm going to be using Rapid Tap. It's been around forever. And I'm not sure if it's the best, but it's what I'm using. It seems to work pretty well. So let's go ahead and put some threads in. I'm gonna try and clean off the tap every time just to make sure you don't have any gunk in it. Alright, well, that's due. It's going to be more of that for the holes that are remaining. So after that's done, we'll move on to the next step. I'm going to rappy tap tap away. So I flipped over the optical breadboard. We can see the end of the broken tap right there. Now, I'm sure there's a couple of different ways to get that out. The problem is that we got a very hard metal and a soft metal, so we can't really drill it out or anything else like that. So I'm going to go and I'm going to try a trick of my own. So I've got a diamond bit on the Dremel here, and diamond is harder than steel. So if we can take and carefully go straight down with this diamond bit, hopefully we can get that out and cleared. One additional 632 tap later, and I have all the holes for the fans drilled and tapped. So I've got them held in with 2 screws each right now, just to give me an idea where they're going to be while I place stuff on the optical breadboard for further marking, drilling, and tapping. So over on this section right here, I'm going to start, and I am going to put the power supply for the red laser right against the side of the laser case right here. To make sure there's clearance for any kind of power filtering plug-in nonsense we need. That'll sit right there. Plenty of room. Alright. And I'll probably end up making another power supply filtering fuse board. Maybe, maybe not. We'll see. That's rated for 10 amps. That's not enough. So, you know, bridge when we get there. Anyway, put the power supply here. That looks good. And then the galvanometer power supply for the scanning mirrors. So, put that probably right here. I want to have the mains on the same side. So, okay, yeah, no, that's perfect. Make sure that we're not trying to drill into holes that are already there. Line those up a little bit. We'll keep that off. About that much. And over here, looks clear. Looks clear. So that's a pretty good placement, I'd say, for those. And then we have the galvanometer amplifier. So that's that right here. And we're going to put this down near the output side of this power supply. And right by where the galvanometers are going to be in this section. So once again, along this edge here, make those wires pretty short. Let's center that here. Make it look nice where those will line up. So yeah, okay, so let me see here. We're going to use some of the rods, threaded rods that I pulled out before as kind of guides, so we can hold things where we need to be. We'll keep it centered like that. Actually, no. Yeah, we'll do this. We'll do this. Keep that like that. Perfect. All right, I'm gonna mark out the holes. I am going to use these right here. I have standoffs on, and give me a little bit of space. I'll put them over here, like this. And I want to keep some room on these threaded holes right here, just to make sure that I can use them. I'm going to move the laser head up front quite a bit. Actually, put that there. Yeah, that's about perfect right there. So go ahead and get an idea of where the galvos are going to actually go, how much room we need for that. Okay, so we need enough room for the height adjustment mirror, which is probably going to about take up that much-ish room, and then the shutter and galvos. So galvos are going to be about that. Yeah, no, that position would work. I think that position would work very well. So, and let's see what we need for the back. Slide it up. Scoonch more. Nah, that really is a good place. Okay, let's call it. I'm gonna mark out where I need to drill and tap those holes. Okay, those are marked out. Now for the blue laser head. Take these off since I don't need them. We're gonna use them maybe for the next laser heads. All right, so here's the blue, and that's gonna be about the same distance from the front, so that's good. I'm gonna get the green laser head as well. And I want a little bit of space because there's fans that are in the case over on this section here against the inside, so gotta make clearance for that. And B, the green may be upgraded. There's only a 15 watt green, and the customer may put in a 20 or 25 watt green, so we need to make room for that. Let me move this up real quick. Alright, so as I was saying, we got fans right over here on the side of the case that are on the inside, so we're going to need about 1.5 inches of clearance for that. So we're going to need to make note of that. Plus, the customer might put in a larger green laser head, so nice to have a little bit of extra room in this area. But we also have to keep in mind, got the heat sinks, so they're going to be underneath that. And if we can get these centers, that'd be better. So kind of get a rough placement for where we want things. Yeah, I like that. I like where that sits. So I'm gonna mark that out, and that'll be that. All right, all the holes for the lasers are now marked out, and I can go ahead and drill them and tap them. All the difference is I'm going to use an M4 tap and not a 632. So yeah, metric side up on this side, and I guess the bottom is standard. Metric's the way to go. All right, cool. I'm going to take off all this, take out the fans, tap and drill the holes for the laser heads and the laser power supplies here. We'll get back to some of the other holes we need to tap for the power supplies for the green and the blue laser heads. To my knowledge, there's only two more things of which will require marking, drilling, and tapping, and that's the switch mode power supplies for the green and the blue laser head here. Now I want to put the power supplies behind the laser head. Let's take a look at the power supplies and consider some options. So they're made by two different companies, but they're pretty alike as far as form factor. So one option is that I could mount one onto the optical breadboard like this and use standoffs to mount the other power supply like this. But I think I'm going to mount them sideways like this, and I think there's an advantage to it. So if I have standoffs, if it gets shipped, the standoffs can move around freely like this, and I kind of want to cut that down. We'll be using standoff later, but for the most part, I'm going to cut that down as much as I can. So what I want to do is I want to screw them together. I got these little cutouts here, so I want to screw in a nut, hold them together, and that'll give them a little bit of a brace against each other, so that way they don't, move around. They have a really good fixation on the optical breadboard. So they'll be sitting up right about here. I say it would be a good spot for them, and of course I want to have access to the threaded holes on the optical breadboard here, because I'm going to have to make a duct for the airflow coming from behind the laser going down into the bottom. So having access to these is vital as well. So yeah. Now the other advantage to this is I have all my live, neutral, and grounds on the power supplies really close to one another. Same as we saw with the Galvo power supply and red switch mode power supply as well. So I'm going to go ahead and screw those together and then mark the parts where I need to put the holes in. Now, time to make some threaded holes. At this point, I think there's only one more thing to do before I start reassembling the laser, and that is to install the 10 heat sinks in the bottom area. So under the laser, there is this bar right here that goes all the way around, and it supports the optical breadboard from the bottom. So you're looking at the bottom of the optical breadboard. The lasers will be on the other side. I've got my green, blue, and red heat sink stacks here that I'm going to mount. The bar is 1 inch deep this way, so I have 25 millimeter tall heat sinks, which is just about perfect to match up to 1 inch. The 5 fans are going to be mounted on the top of the optical breadboard, blowing out into the bottom, and there'll be a piece of metal that goes over all of this that will duct the air out and this way across the heat sinks. To show you that, I'll put this piece of plastic over, which will show you how that will work. So it'll sit like this, and the air will come this way and out the bottom. We're going to put bead on the laser too, so it's elevated by about 1.5 inches, maybe 2 inches. That way the air can escape. With the heat sinks here and the heat sinks here, I could pretty much just drill my holes as I want to. Don't have to worry about any kind of conflicts. So what I mean by that is there's no holes in the center right here or right here, so I can just drill 2 holes on the center here and here, and on the sides there's not really any kind of conflicting area either, so all of this is free and all of this is free. Let's take a look at the 4 heat sinks for the red here, and we do have some conflicting holes. So if I remove this heat sink, actually before I do that, I want to note that the center right here is lined up with these set of holes here, so if I have a conflict, it's going to be along here. Now if I remove this heat sink and move it off to the side like this, we can see where those holes would be. So there's no conflict here, no conflict here, which means that I'll be able to do this one with the 6 holes that I want to, 2 in the corner, 2 in the middle. We'll go ahead and remove that one. So let's do this. Let's see where those holes are going to line up here. And you can see that right here we have a hole, and right here we have a hole. So for the center of this heat sink, I want to drill the holes and tap them closer to the center instead of being on the outside, and so on and so forth, like this. So take a look at that one. Yeah, it looks like I have a little bit of a conflict here. Other than that, that's what I'm going to do. So I'm going to put these back into position, and I'm going to do each one of these independently. And then I'll just go ahead and do all 6 holes in these. That'll be easy. Line that back up again to where it needs to be. Right. So, yeah. 120 holes that I need to drill. 60 of them I need to tap without breaking the tap. But that's what I'll be doing. And I'll do little video segments of just the progress as it goes. But you see me drill holes. You see me tap holes. Yeah. So, I'll come back mostly when it's done. I now have my 60 holes drilled in all the heat sinks, and it's time to go ahead and mark on the bottom of the optical breadboard where I have to drill and tap for the screws that will hold them in position. I have some Scotch tape along the edges of the heat sinks just to hold them together in groups. And let's go ahead and see if I can get the 1-inch nib down in the bottom of the 1-inch heat sink and make some marks. Let's go ahead and do that. And do a final check on our marks. Make sure they look good. Yeah, it looks like all the marks for where I need to center punch, drill, and tap the holes for all the heat sinks turned out really well. So I'm going to go ahead and do that monotonous task. I'm ready for it. And then we can start putting this laser together again. You know what time it is? It's finger painting time. Alright, I got a lot of thermal paste here. I'm going to go ahead and use quite a bit of that and install the 10 heat sinks on the bottom of the laser. So, it's going to be part making a MOSFET thermal compound and hoping that all the holes are drilled and tapped within a millimeter of precision. Right. Wish me luck. Time to get messy. Alright, looks like I just have to rework this hole a little bit, and rework this hole a little bit, and then it'll all clamp in very nice, feels smooth, that's good. Another thing I'll do is I'll let the heat sinks sit for a while, let the compressive force kind of spread out the thermal paste. I'll also come with a heat gun and heat up the heat sinks, which will raise the liquidness of the viscosity, lowers the viscosity of the thermal grease, and that also helps it to spread out evenly. So that's another thing. 2 things I'll do: clean up the holes, warm these up, clamp these down fully, make sure they're good. I'll do that off camera, flip over the laser, and we'll start working on the top side of the optical deck. Time to start working on the business side of the optical breadboard now. And since I've just finished installing the passive components of my cooling solution, it's time to install the active ones, and that's the 5 fans. So here's those, and we're going to need some screws, and some nuts. Now, the reason why I'm using nuts is because these are vibrating components, and if they vibrate, the screw can work its way out of the tapped holes, and the nuts will help secure it in there a little bit harder. We're also going to need some tools, so some screwdrivers and a wrench and socket. So let's go ahead and start installing those. Yeah, those ain't going anywhere. That looks fantastic. Alright, next thing is probably power supplies. So, go ahead and work on installing those over here along the side. And now we may and or may not run out of the correct screws, but we'll see. So those are all my M4s. I am short on short ones, so I've got these. Alright, I'm going to need short ones for at least these holes here. So, we'll go ahead and put the short ones in just for now. And put longer ones in here. But later on, probably take them out, put shorter ones in there. Go ahead and do that. Alright, flip that around. Oh, that way I can have my mains in close to one another. Okay, that's in. Looks good. Galvo power supply. All right, I'm gonna go ahead and install the two power supplies up here for the green and the blue lasers. Move that over. And I want to probably elevate this a little bit off the optical deck. Maybe, maybe not. You know what? For now, we won't. But if it gets too warm while operating, we'll see. Oh. All right, socket screws obtained. Socket screws, cup screws, set screws, headless screws obtained. Start putting those in. Now, the screws that I'm putting in here, between the heat sinks and the lasers, they're not really preventing any kind of airflow, but just the fact that you have a little bit more metal in there, instead of just being a bare hole, I'm sure will help thermal conductivity just a little bit, although they are steel. So iron is not the best for thermal conductivity. We make do with what we have. Iron is better than nothing. Well, this is what I'm going to be doing for the next, say, 10 minutes or so, so I'll get back to you when this is done. At this point, I can go ahead and install the 3 laser heads now, which will require a little bit more finger painting. But because I want to keep the laser heads as clean as possible, I am going to wear gloves for this round. Go ahead and do that. Alright. And grab a laser head. Actually, we're going to grab all 3 of them at this point. I have wiped down the optical breadboard just to make sure that there's nothing that will be sticking up, causing a problem. And deburred all the holes that I tapped. So we lay the laser head on there. Try to make it rock. It's as silent as can be. So that's exactly what we want to see. Flip over the red real quick. We'll lay the green and blue down as well. Try to keep these out of the way as much as possible. So here's the blue. And then the green. All right. Go ahead and make sure that those are all clean as well. Can't be too sure. Green looks like it needs a little work. Yeah, that one looks good. Red looks good. Yeah, just the green. Okay, let's go ahead and lather those up with some thermal compound. A huge mess. A huge mess. There we go. Well, that was a fun mess. Go ahead and take off the gloves. Uh-huh. All right, let's go ahead and install some laser heads. So, first starting with the red. Next one, the blue. This one's going to be a little trickier because I got the cord pressed up against that power supply. There's going to be an abundance of thermal compound in that hole. That's okay. We'll take care of it regardless. We'll move on to the green. And of course, after the laser warms up and we run it for a little while, go around and screw those screws down a little bit more. As I said earlier in the video, when the thermal paste is warm, it becomes thinner, less viscous, and we can often get a quarter turn to a half a turn more on each one of those screws. So let that sit for a while. Alright, make sure everything's all clean and nice otherwise. Don't really worry about the thermal paste around the edges of the laser too much. It's going to squeeze out a little bit anyway. And if you watch my channel, you'll notice that it's quite common to see a little bit of thermal paste like that around large laser heads such as this. So it's part of the nature of using that much. As I mentioned earlier in the video, the aperture for the red laser is higher off the surface of the optical breadboard than the aperture for the blue and the green laser. Now, we could use a metal plate to bring up the blue and green lasers to match the output of the red, but instead I'm going to use two high-quality first surface mirrors in a custom optical mount. To show you the effect that I'm going for, I'll demonstrate it with two right-angle prisms. Now, due to total internal reflection along this surface here on the inside of the prism, we can see things at different angles. So for example, let's see if I can show you. So that's the light on my ceiling, and it's acting like a mirror. So we're going to use two mirrors, and our configuration is going to be very similar to this. So we have one reflecting surface here, reflecting surface here. Now, if I put that against the output aperture of the red laser head over here, you'll notice that we can see a reflected image of the aperture right here. And if I move this, I can lower it down or raise it up. So that's exactly what I'm going to do with two first surface mirrors. So let's go ahead and make that custom mount. To make the custom optical mount, I'm going to use some aluminum square channel tubing that is 1 inch by 1 inch, about 25 millimeters by 25 millimeters, with a sidewall thickness of about 1/32 of an inch or 1.5 millimeters. Anyway, we're going to need to make two main cuts. So we're going to need to make an angled cut like this, and the first mirror will be on that cut. So laser light comes in this way, gets reflected this way. We need to keep some room, so that way we can put a screw or something in there to mount this portion of the optical mount. And then over here we need to make another cut at a 45-degree angle. So laser comes in this way, goes past our mounting point right there, hits this other mirror and out the front like this. Now our marks are going to need to be a lot cleaner and better measured than this, and luckily I've already taken the time to do that on this side. So go ahead, put this in the vise and start our cuts. Yeah. So the vise is not exactly known for its triangular cutting capabilities, but go ahead and do what we can. I've got about 2 and a half foot of tubing sticking out the other side, so it's a little cumbersome right now. Just kind of realize that I should be cutting the other way, but I'm right-handed, so what do you know? It is the way it is. Alright, that looks good. Let's start our cuts. It'll take a while. We're doing this manually, and we have things in the way. Not anymore. Here we go. Alright, now to do the other side and wash out the dead spider. Yeah, that's quite nice. Now the only thing to do is wash out the dead spider. But this is what our piece looks like so far. Not too bad. Here's what I have so far of the custom optical mount. And I sanded these two sides to make sure they were level and smooth. The next thing to do is to cut out the section of aluminum here, because the laser needs to come in this way and then reflect off. And I can't do that if there's metal here in the way. So I'm going to make it as square as I can, mostly. So I'm just going to use this, about the same size. And mark it like that. Move it over, do the same thing. I bet you can get where the marker cap is. Not in my hands. Alright. And we do the same thing on this side. Just like that. So, to make this real easy on myself, here's what I'm going to do. I am going to center punch holes along this area, or center punch, and then drill holes along here. So that way, when I cut down with the hacksaw on these two sides, I can easily bend it, pull it out of place. I don't feel like moving the camera, so I'm going to do those holes on the drill press and then come back with the hacksaw. As you can see, I have some holes now drilled there, and they don't need to be pretty, they just need to break. In fact, that's why they're there. So I'm going to go ahead and clamp this in the vise and cut these sides down with a hacksaw. You can go ahead and bend this out like a tab. Should be pretty easy. So, it looks pretty good. I wish I could clamp this into the vise and trim this down. Sadly, I will be cutting off, or trimming down this right here, and I'm going to keep that. So, that's going to be a bit of a tricky one, but I think I can do that with the Dremel. So, I'm going to go ahead and try to clean that up a little bit. At this point, I finished the portion of the optical mount that'll hold the two mirrors on. I also took an M5 screw and I put it in the lathe, and I took the head off so that way it's real close to the outside. So I've got plenty of clearance for the laser beam to travel through there, and I've got plenty of thread on here to mount it on whatever bracket I need to. Now we're going to need to clamp this to the optical breadboard somehow. I've got one of the mounts that I pulled out of the laser. So figure, let's see, the laser is going to come in this way, get reflected off this way. So whatever bracket I make, it's going to need to have clearance on this so the beam can come out. So figure the bracket's going to sit like this, and it's going to tie this and this piece together. I want to be able to make a couple of adjustments. I have this cut out right here, which will allow me to do any vertical adjustment, but I want to cut out on the bracket that'll join this and this together to give me a horizontal motion so I can translate the beam wherever I need to. So I'm going to make something that's, say, like this. Going to have a little hole here, and then I'll be able to do this with it. So a little bit of a piece to make. I have some aluminum stock right here, and so we can kind of get an idea of what we're going to make. So probably going to be like a teardrop shape. So one portion is going to have a small hole to clamp onto this piece like this, and then we're going to have a larger section here to clamp onto here. So figure if we come this way like this, and then that'll be our cutout for the horizontal, like say right here, and then the whole piece will end up looking kind of like this. Terrible picture, but something like that. And you know what, I'm just gonna freeform cut this out in the saw because it's not a complicated part to make, and I'm gonna use my artistic instincts to do that. So as Mark Kissel would say, saw, 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 saw. Alright, at this point, I am going to drill a hole here and a hole here, and we'll come back and finish this. Holes drilled, let's get back at it. Yeah. Can I get this? Probably not. Yeah, I'm gonna go at this with a file now. Turn that off. Alright, we can go ahead, drill that hole a little bit bigger, clean the rest of it up with a file, make that piece look really good. Alright, so here's that part. I went and filed around the edges, made it look pretty good. Let's go ahead and check it out. So it'll go like this. Yes, laser comes in this way, reflected this way and out. So plenty of clearance here for the laser beam, it looks like. That won't be a problem. Go ahead and put this on. And that'll link up like this and there. So I have plenty of adjustment points of which I can use to translate the beam where I need it to be. So yeah, looks good. Unlike my hands, which are absolutely trashed. But hey, this will look better after I get done sanding it. And things need to get a little dirtier before they get cleaner. So hopefully next time I come back, this part will look nice. So will my hands. Yeah, you know what? We'll do some sanding on camera. Just for therapy. Yeah, that that really does look nice, doesn't it? I think so. I think so. At this point, I have everything mounted on the optical breadboard that I need to mount on it, and I can go ahead and start with the plate that goes over the laser heads and supports the laser drivers. So at this point, I have all these 1/4 inch threaded rods that are mounted in the optical table. Right now, they're just place holding, but they'll be properly installed and secured after I process the plate. Let's go ahead and take a look at the plate, which is 3 millimeters thick, about by 1 foot by 2 foot, and that'll go on those threaded rods like that. I'll drill holes, lock them into place with nylon lock nuts, and that'll be pretty secure. You might be wondering how I'm going to stop it from wiggling around like this. Well, I've got a plan for that too, and that involves this aluminum L channel. So I'll cut some pieces of L channel like this, screw it down here so it holds onto the plate, and then it'll also be screwed to the side panel of the laser, which will prevent it from rocking back and forth. So this is going to be held on really good and secure. Now, the laser drivers are going to be mounted on the top. So not only do I need to drill the holes for the threaded rods, but I also need to drill and tap the holes for the screws that'll hold on the laser driver. So the green is going to sit over here above the green laser head. And the same is going to be done with each of the other laser drivers as well. So like that. And then the two for the red laser module accordingly. And then another L channel on the side. I need to cut out a little bit of this corner here. I'll show you why. So on the inside of the laser, there are fans, and I need to make clearance for that. So that fits on. You can see where that hits. So probably cut about 1.5 inches off this corner and out a couple more inches. You know, probably do a diagonal cut here. Be the easiest and probably look the best. So that's my plan. At this point, time to drill and tap some more holes. So I went ahead and I drilled the holes for the threaded rod to come up and through, and I set the height on the nylon lock nuts so those are all even. Now I have the laser drivers here positioned and mounted where I want them, and you can see that. I've also did my center punching, and I'll drill and tap those later for the screws. But you'll notice I have them spaced out, and the reason why I have them spaced out is because these laser drivers have transistors that operate in a linear range. What I mean by that is we got DC to DC converters over here, and those step down the voltage from 12 volts to the voltage and the current that the laser diodes need to operate. Now we adjust the brightness of the laser diode outputs by these transistors here on the side, and as I said, they operate linearly. So when you want the full power from the DC to DC converters, you want the transistors to be as conductive as possible, and they don't get very hot because they're not dropping a lot of voltage. Current times not a lot of voltage equals not a lot of wattage, not a lot of heat to dissipate. But say if you're using the lasers at half brightness, well, the energy needs to go somewhere. And what happens is that we change the conductivity of these transistors. We make them more resistive. So that means they act like resistors, like bleeding resistors. And they have to dissipate the power somehow. And they dissipate the power by turning it into heat, like resistors do. So the laser drivers are spaced out just to kind of help prevent any kind of overheating due to close proximity. Gives them a little bit of breathing room. Now, I'm going to give more structural support to this plate as well, because we just got these 8 rods, and that's all we're relying on. The plate can move back and forth like this, and I want to make sure that doesn't happen. This thing's going to be shipped at least once, and it's going to be taken to different venues and toured around, so it's got to be as strong as it can be. I want this thing to dent the earth if it drops. So that's my goal. To help with that, I'm going to take advantage of the size of the lasers here, and I made a couple of L mounts like this, L brackets. These aren't fully done, but I'll go ahead and finish those on camera later on. is one more that I need to make from scratch anyway. Well, each bracket will have 2 screws holding them onto the aluminum base down here. Move that up so you can see. So 1 screw here, going down. And then there's going to be a hole in the bracket and a hole in the outside of the case, the side here. And there's going to be a 1/4-inch screw that comes in and locks the bracket, the mount, to the plate and the outside. There'll be 3 brackets like that on this side. Now 1 more in the middle right here. And on this side, there will be 2 brackets. So 1 bracket here and another bracket here. And same thing for the brackets on this side. So 1 screw, 2 screw, and the screw coming in from the outside this way and locking the side of the laser to the bracket. Now we got a little bit of room here, and I'm going to use that to my advantage as well. So this is a power supply for the fans. It's a 12-volt, 30-amp power supply. It's about what we need for these fans. And I want to make sure that this is also mounted as structurally as we can do that. Now, the best holes to use in most cases are the ones on the bottom. You want to keep your center of mass low, so that way it doesn't, vibrate and shake around. However, with these power supplies, you only got about 2 millimeters, if even, from the outside of the screw hole down to the PCB, and the only thing between the screw and the PCB is a little piece of plastic. So, for example, if this is in the laser and the laser takes an impact this way, that means this is going to get hit, and there's a chance that these screws, the standoffs, are going to get dented inwards, and they're going to make contact through the plastic insulating barrier, maybe short out the power supply. So I kind of want to avoid that and avoid using all of these holes. The best side to mount on is probably going to be this side. It has 4 screw holes here. The other side only has 2. And my thinking is that I'm going to put 4 holes in here and mount this power supply like that. So there will be 4 screw holes coming in from the bottom of the plate going up, screws securing this to the plate, and then there'll be a screw here and a screw back there on those standoffs coming in from the outside of the laser side here. So that gives us 6 points of holding. That'll prevent any kind of fumbling and wobbling like this, and give it a nice structure down here, and also plenty of breathing room. So that's the way I'm going to do it. I'm going to remove this plate. I've got a couple of holes to mark, drill, and tap. I've just finished some much needed tasks before I can get this all put together. So, a couple of things to go through. I've wired up the AC side on here, and I've wired up the AC side on here, and I've drilled the holes on the sides so that way I can lock in the plate. Here's the plate. So these 4 screws are holding the power supply in. I've got these all mounted down. The L brackets, it looks good. Flip it around, you'll see that the power supply is right there. Got the standoffs along the side. Let's go ahead and start getting this thing put together a little bit more. So I'm going to drop this down in place. Set it on those threaded rods. Down you go. Right. Let's go grab some screws and nuts and start some assembly. Right. That looks good. So I've done a fair bit of work, but there's still a fair bit more to do. Besides, I still have uninjured portion of my hands, so plenty of me to still go around. Next thing I want to work on is the fan shroud. So that will be a box that gets connected to the screw holes on the bottom of the optical breadboard right here. And we'll come up, and then we'll do a 90 and go over. I'll put holes in the back of the laser, so the air will come in through those holes into the fan shroud and then get directed into the bottom of the laser. The fan shroud will be simple construction out of plastic and aluminum L channel and should go together pretty easy. Besides, I've already fabricated the parts and indexed them, so it'll be practically IKEA level of assembly at this point. Let's make a fan shroud. So, to start off with, I have these 4 pieces that I cut out of plastic. Now, it's really easy to cut this kind of plastic. What I do is I make my measurements, I get a straight edge out, and use a box cutter or some other sharp tool to score along the straight edge, and you can snap your pieces out pretty easy. You'll also notice that the holes are drilled, and I have little index marks for what piece that goes to what piece. So 4 here, 10 here, 8 and so on all the pieces. That way I know how it all goes together. And to hold those pieces together, I have extruded aluminum L channel. And I just kind of cut this and measure this as needed for the box that I'm making. So yeah, and these are also indexed as well. So see a little 5 on there, 3 on there, so on and so forth. So should be pretty easy to assemble. To hold the parts all together, I'm going to need screws, washers, and nuts. So I have these. I'm going to use the shorter screws for the area where the fan is. That gives me a little bit more clearance. And the longer screws for the rest of the box because I have them. So that's why. No other reason besides I have them. And a little bit of Loctite. So that way it doesn't fall apart when the fans start to vibrate it around. And tools. So, yeah. Let's put this all together. Should go pretty quick. How do I know where to hit it when there's no 57 on the bottle? Alright, that's it. Let's take a look and see how it looks. Looks good. Looks really good. Time to clean it off. Clean myself off. So I just got done installing the finished fan shroud on the optical breadboard. That's right here. Now, this might visually look like it's at an odd angle, but that's because currently the laser is resting on its front, which will give us an excellent view of the rear and the bottom of the laser. Now, before I installed the fan shroud in the laser, I also did one more thing, and that was to install this piece of plastic on the back corner at a 45-degree angle. The reason why I did that is because when the air comes in through the back, it'll hit this plate, and it'll deflect the air down through the fans and into the lower compartment under the laser. At this point, I'm almost ready to move on to the wiring step of the project. But before I do that, I want to finish off the cooling and most of the structural aspects of the laser. The biggest thing to worry about, as far as that, is the plate that goes onto the bottom of the laser, which does two things. First of all, it's part of the active cooling solution because the air that comes out of the fans this way needs to be redirected so it flows across the heat sinks. The plate will do that. The second thing that the plate does will help add rigidity to the optical breadboard so it doesn't bow or sag. Earlier in the video, I installed 8 threaded rods, and those are currently supporting the plate on the inside of the laser that the laser drivers rest on. But in this case, I'm going to do dual duty with those. And on the end of the threaded rods, I installed these appropriately sized standoffs. The standoffs will help hold the plate on the bottom of the laser and will also hold the plate to the optical breadboard, giving us that added rigidity. Now there's 4 standoffs down here, and there's 4 standoffs here. The plate that I have is 18 by 24 inches, which leaves us with about 5 inches of venting space on the front of the laser and the bottom for the air. So I'm going to go ahead and put this plate on and show you that. And I'm just going to use 2 screws real quick. Alright, so as you see, the plate covers most of the bottom, leaving about 5 inches down here for the air that comes through the heat sinks to vent out the lower front of the laser. It's a great design as long as this is not resting solidly against the ground. So another thing that's mandatorily needing to be installed is feet. In fact, this whole project rests on them, quite literally. So I need to make 4 feet to go on the bottom, 1 foot for here in each of these corners on the plate. Those will be held in with 2 screws apiece, and of course I have to do the drilling and tapping for those screws to hold them in position. So that gives us 8 screws, 1 for each one of the standoffs, and 8 more, 2 for each of the corners. So in total, 16 screws that'll be holding this on. So that should give it plenty of support for its touring days to come. Let's go ahead and make some feet. Making feet for larger pieces of equipment is actually pretty easy to do, and there's a simple design that I'll be using. So here's what that looks like. I've cut a trapezoid out of a piece of aluminum square tubing, and I have 2 holes drilled in, which will be the top of the foot. So screws will come in this way and hold it to the bottom of the laser, and we have some rubber sticky pads that we'll put on the bottom, so that way it doesn't scuff up any surface that it rests on. So let's go ahead and make that. So I have this section from the feet that I made before, and I'll just use this as a measuring block. The first one's the hardest one to make, and it's all downhill from there. Get the marker. Just like that. We'll go ahead and cut that out on the saw. Alright, and I'll go ahead and clean up those edges with a file. It's time to spray paint some feet. So I have my 3 unpainted feet here, and each one of them has a little piece of tape on it. This one's black because I've already done the first one. Let's take a look at that. So here's that bare metal section after the tape is removed. And the reason why I have the bare metal here is because I'm going to put little adhesive pads on the bottom of these. And I want the best contact I can have. So it's all about cutting down points of failure. And there's a point of failure between the metal and the paint as far as adhesion. And I don't want that. So I want to have those sticky pads stick right onto the bare metal here, cutting down that point of failure. I think that'll work out better. So let's go ahead and quickly paint these feet. All right, we'll let that dry. While the paint on the feet dry, I'm going to prepare the bottom of the laser. That way I can screw down the feet when they're ready. What I'm going to do is center punch, drill, and tap these holes. There's 8 to do. So to do that, grab the center punch, find center, give it a whack with what's left of my hammer. All right. Down here, do that again. Good. Walk that one down a little bit. That'll work. It's drilling time. Now I don't want to drill all the way down. I just want to drill enough to tap the holes for the screws. So on the drill bit, I have a little plastic tube, which will prevent me from going too far into the laser case. And that should help. So go ahead and start with that. Start drilling. Whew, right, I'm gonna finish that without the camera in my way. Oh, check this out. So I just got done putting on the finished bottom plate and the feet on the laser, and it looks so good. I am very impressed with how that turned out. So I went ahead and spray painted that and the feet, made sure those look good. I put the little rubber pads on the feet. Of course, we got those 8 screws here that hold this plate under the optical breadboard with those standoffs and threaded rods. The air that's pushed in by the fans in this section gets blown down this way across the heat sinks and vents out the bottom here. Now I've got the holes in the optical breadboard for threaded inserts or 1/4-inch screws, and in this section here I went in with all those socket screws, and every hole that was open I plugged, so that way the air that's in this compartment won't get pushed through those threaded holes and into the optical bay. So this is now a sealed compartment from that section. It should keep all the dust out. At this point, I am ready to start the wiring. So I'm going to go ahead. I'm going to put this laser on its brand new feet, and we're going to start probably with wiring up the fans, get that all set up. That looks so good. Time to start the wiring, and I figure may as well start with the fans first, because let's face it, without those, nothing is going to run for very long anyway. Let's take a look at what we have. Inside here, we have our 5 fans, and there's some wires and stuff. So first thing is these yellow LEDs. I'm just going to cut these off, put them in my miscellaneous LED bin, and save them for my own nefarious use in the future. We have these connectors here, and on each connector there are 2 black wires. Those are just joined together right here. We have the red, which is our 12-volt positive, in reference to the black, which is our negative. Then we have a yellow and a green. Now the yellow is a tachometer signal out, and that tells like a microcontroller or whatever how fast the fan is actually spinning. So that's a signal out. And then we have this PWM input here, which is the green wire. And we'll be actually using that to control the speed of our fans. I'll show you the board that I made to do that later on in the video. But we have 3 wires that pretty much run. That is the negative, positive for the 12-volt DC in, and then the PWM duty cycle controller input as well. So let's go ahead and start with that. Okay, so I want to try to have an even load. So I'm going to run heavy duty speaker wire through here to the center, and I actually want everything coming to the center. A little bit of extra length on the speaker wire, but I don't want to wire here and then wire here and wire here and then have a voltage drop by the time we get over to this side. So we're going to avoid that. This is the wire that I'll be using. pretty okay stuff. I made sure that it's not simply copper-plated aluminum, because they do that. Did you know that there was a heat shrink cool tax? The white heat shrink is cheaper than the black heat shrink. At least at Menards it is. Alright, now that we have all that set up, it's time to run the main wire in from the holes on the outside of the fan shroud. Let's do that. And I'm going to show you a real cool trick. So you know when you take apart CD-ROM drives and stuff like that, they have the little rubber cushions on the optical assembly that are vibration dampeners. Well, they make great wire grommets, so yeah, reuse them. Pretty nice. Alright, what? I know one of these says positive. Yes? No? No? No. Well, we'll have to mark that. What do you know? Okay, now to run the wire that I'm going to use for sending out the DWM speed control signal. I'll be using a little piece of audio signal coax. Alright, and that'll isolate the signal pretty nicely, I think. And that looks good. Okay, so what I'm going to do next is just put a little piece of heat shrink on these 3 loose exposed wires. Just to tidy those up. Alright, run that wire through that hole. Yeah, no, that looks pretty good. So, I'm going to zip tie these wires on the fans, tuck them all in, make sure that they don't rattle around. So here are the fans. They're all wired up and zip tied to the fan housings. They look really good. I'd say it's time to connect power and get these fans whooshing. As I mentioned, when wiring the fans, we want to be able to control their speed. That's for 2 main reasons. The first main reason is if you don't need all the cooling, why run them? Wear down their bearings and the power supply and put extra stress on the unit when you don't need to. Second one is the noise. So say for example, you're doing a professional presentation or doing a stage performance like a play that has a lower noise floor. You don't want to raise that noise floor and make a whole bunch of noise with all the fans and the laser, especially if you're only running the laser for say a couple of minutes out of that entire performance. So that helps with that as well. To control the speed, I made this little board which uses a 556. It's a dual timer, and there's a handy video that I saw which goes over how to make most of the circuit. Now, I'll link that video below in the description. However, the one modification I made to that circuit is we have the speed adjust potentiometer right here, which sets the duty cycle. But over here, I have in series a optical isolator, a photocoupler. And what happens is when a NTC thermistor changes its value as far as resistance, it'll control the conductivity of this NPN transistor, which is a D822. And if you want to learn more about this, I can make a video on how this whole board works. This is one out of 2 boards I'll be installing, but yeah, not really much to it all in all. Right here I got my sensitivity temperature adjustment right here. It works really well. And of course on the end of this wire here too, I have my NTC thermistor, which I can just mount on the optical breadboard. So it should work pretty nicely. And once again, as I said, if you're interested on how to make this full board, I can consider making a video on it in the future. So I'm going to go screw that board in. And then I'll finish with the wiring. So now I have to connect the main wires right here, and I also have to connect the wires right here. I'm going to do a sanity check before I do that. Crank power through there, see if I got my P's and Q's crossed. It's meter time. Alright. Power ground and the signal ground should be connected. Okay. Power ground, signal ground. And they are. Nice. Okay. Awesome. I got my 12-volt power supply here. Let's go ahead and connect it. Okay. Now, according to the service manual, which rests solely inside of my head, once we connect power to this power supply, we should be able to power up the fans and see how they run. Check this out. We'll heat it up a little bit, not too much. Yeah, that's thermal management. The fans got me. They're definitely doing their job, and that's on low power. But that's just one of the many fun injuries I've received while working on this project. Let's go over some more of those. Got that one when I was double checking the aluminum plate here, the bottom plate, when I picked it up from the metal supplier. That was fun. This is where I filed over my finger when I was finishing off the legs of the laser. These 2 marks right here, that's from the hacksaw, as I was cutting out some of this L channel right here. Got a stab here in my palm, that's from cutting the plastic out, and the box cutter blade got me a little bit. That's nice. Burned my hands with a soldering iron and hot wire a few times by now. And yeah, from all the hand washing during the project as far as the machining, getting the lubrication on my hands, all the other aluminum short, stuff like that. Yeah, my skin is wrecked. It's as dry as the Sahara. I could give a cat's tongue lessons. The next portion of the wiring I want to handle is for the red, green, and blue signal modulation. And that comes in from the DB25 analog ILDA input here. There's wires that come in through the back and run to these potentiometers. We got blue, green, and the red is not even hooked up. It's because red wasn't installed in this laser at all. And then wires that come out from those potentiometers. So these potentiometers just basically act like a voltage divider. On one side you'll have common ground between the signal in and signal out, and then you have your signal in positive and your attenuated signal out from the sweeper in the middle. So pretty easy to wire up. That means we have 3 wires that come in from the ILDA port, which are these 3 wires here. As I said, the red's up here. It's kind of zip tied to a plastic sticky bracket. I'll move that over to the potentiometer where it's supposed to be. And I got these 2 wires here coming from the green and the blue. Those will be replaced. So I'm going to use this audio coaxial. The reason why I'm using coaxial is because I want to keep the noise floor down on those modulation signals. So I'll go ahead and install those real quick on the potentiometers. Get that all wired up. So if you take a look at this right here, we have our input positive for the signal modulation, and then we have our negative here. The negative is going to come over to this side, and we're going to join this negative to the negative that's going out, which in this case is the outer shield of this wire. So take this, twist it together. Nope, that's the green. What am I doing? Good catch, you guys. Alright, and that's going to go to the sweeper. Go ahead and heat gun. All right, that's done. Our 3 color wires, and those will go out to our delay board. Let's talk about one of the requirements that the FDA has as far as laser products are concerned, and that would be a startup delay. So they don't want the laser to come on right away, just in case you're still setting it up or doing whatever checks you need to. So they want at least 30 seconds before you can use the laser. To do this, I have made myself a little startup delay board. It's a very simple delay circuit, just uses a 555 timer. And I can also put information about that as well in the description below. And then I have 3 relays here, one for each color. Now the reason why I'm not using something like a transistor or a MOSFET, when you use a transistor, since it's current controlled, a little bit of the noise from the power supplies can get into your signal line, and MOSFETs tend to fail short. And we want this to fail safe. So, yeah, relays are the way to go, in my opinion. So, very simple board. We have a common ground, so much like the potentiometers, we're going to have input and output ground tied together on this rail. And then we have our output on the other side of this resistor here, the 53K resistor, just to make sure that when the contact is flipping from this to this, there's not a complete disconnect. And then the shared contactor pin, which is on this piece of metal here, is going to be our signal output. So between ground and our signal level, we'll be able to switch between no laser output, and then after about 40 seconds, laser output. So very simple board. If you want me to make a video about making these, I can also do that too in a later video. Let me know what you guys want. But anyway, it should be a very simple board to install. All I need to do is run the color channel wiring and then the 24 volt power. So let's do the signal wiring first. Here are the inputs. Go ahead and a little bit better view. So I want to take all the grounds and get them all tinned up. Bring my soldering iron over. That's better. All right, that's in the way. Not better. Okay, that's better. Better. I also have my wires here. These go out to the laser driver modulation. We'll handle these after we handle the input wires. Okay. And all of these will just go across just like that. Pretty simple. Let's go ahead and start soldering that. So let's start with the green in the middle, actually. Good place for green. And we'll put red down here in the corner. And a blue up here. Okay, just like that. Looks good. Okay. Now for the output wires. So those are all right here. Let's start with the red. And we're going to tie all the negatives together on the same circuit. Okay, so positive goes on the moving pin, just like it would on the sweeper. This is positive out. So, right there. And then we're going to put this on the negative. Okay, next is the green, which is this guy. Come here, wrong tool. Every time. It works every time. Flying camera action away. Actually, can I zoom in? Yes I can. Okay, so it looks confusing, but it's not as confusing as it seems. So all the grounds are tied together. So there's a ground, ground, and then on the input side, right here, that's the other contactor in the relay. So it's normally closed, and that means that the contactor is against this pin right here. And when there's power put into the relay, the contactor moves over to this pin. And on the contactor, we have our signal output. So this is that switching contactor right here. This is that switching contactor, and then again over here on this top for the different colors. So, and you can see that here. So that's the contactor that actually moves. So last thing to do on that is to put power and test it out. Now, there's a couple of other things that need to be added to this to make it capable of applying for a variance, and that is the external shutter switch, an interlock key switch, and a switch inside of the laser, so that way if you take the cover off, it goes off. And I have this long section of wire here. We're going to eventually integrate that into everything else, but right now I'm just going to do a direct run from 24 volts on one of the laser driver rails, and sorry, laser power supply mains to 24 volts, switch mode, power supply, doodads, things. So let's go ahead and wire this up. Okay, power is connected to that. So at this point, since all the switch mode power supplies and everything else is plugged in, I believe I can just throw power onto this, and we can go ahead and test everything out. At least test the well, at least see if the delay works. We'll go ahead and do that first, and then we'll connect the ILDA up to it. See if we can get signal going. Get some laser modulation. All right. Set that off to the side without shorting anything. Okay. Good. Just to make sure, take the tape off of the front of the laser modules just in case they fire for an unknown reason. We don't want the tape burning and destroying the output windows. Okay. I'll flip off the light, plug in the laser. Sanity check. Looks good. Okay. And we got a green light on that. Awesome. Now we wait a couple of seconds. See if that blue light comes on. Right, we should also see the relays actuate. Maybe you can see it, maybe not. I'll tilt that up. That looks to work beautifully. And no accidental laser firing. Okay, cool. So, I'm going to throw some hot glue on there. Make sure the wires don't flop around. And we'll hook up an Elder cable. See if we get laser output. Looks good. To my knowledge, all the wiring for the lasers should now be completed. So let's go ahead and give them their first test run. Make sure everything works properly. Just a real quick rundown. I have my modulation signal coming from my FB3, which goes through the DB25 and up to the potentiometers, which are essentially just voltage dividers of which we can use to attenuate the amplitude of the modulation signal. That goes through these wires into the delay board, which gives us a 40 or so second delay before the laser drivers can be activated. And because I don't have any of the optics installed, nor the galvanometers, all we should see is just the beams coming out of the front of the laser heads themselves. So let's go ahead and test everything out. First, let's see if we meet the 30-second delay of the requirements. So here we go. Okay. We should be good to go now. Let's try feeding it a white. See what we can get. Actually, you have signal going now. So let's go ahead and test red. Nice. I see a little bit of red. I see a lot more red. That works beautifully. Good. Let's test the green out. Nice. That also works real well. And let's see if we can do 3 for 3. Blue. Oh, yep, there it is. Nice. Very nice. Very nice. Man, that's bright. Okay. I just real quick want to make sure that the delay is actually working properly. And the signal's working properly. So let's go. First, let's do the colors. So red only, and this is just through software. That looks good. Let's move to green. That looks good. And finally to blue. Yep, everything's working properly on that. Very good. And let's go ahead and test that delay. I'm going to shut this off real quick. Turn this off. Give the delay board a little bit of time to reset. Okay. Turn the unit on. Turn the signal on. Alright, so when the delay board fires, the beam should turn on. See if this works. Perfect. And now on to more FDA requirements. So at this point, I've confirmed that the delay board works as it should. And the simple configuration I have currently is that these wires come from that power supply down there and feed power to the delay board. Now, we don't want the delay board to be active unless certain criteria are met. And these are the rules. So we have to have a key switch. we have to have an external safety button, we have to have a remote interlock electrically, and we also have to have an internal interlock for the lid switch. So if the laser's open, the lasers will shut off. So I'm going to go ahead and install 2 of those things. I've got the key switch here, and I have the 1/4-inch jack that goes out to the emergency safety shut-off button. So let's go ahead and put these in. How this is going to work is that these are going to be switches, and they're just going to go on one side of the line. So if all of these aren't in the closed position, the delay board won't turn on, and that'll be that. No laser action. A very simple operation. Run this to the outside, and we'll be installing the key switch first. Just say I will be. So you can see those right there. Time to get the soldering iron out. Alright, now I gotta see which is the normally open, normally closed position. So we'll say that way's off, that way's on. Let's see which one is what. I'm gonna guess it's gonna be these 2. Seems to be those 2. And yep, okay. I'm a goofball. I gotta take the nut off first. Are you serious? The threads aren't long enough. That's dumb. That's really dumb. It's fine, it's fine. We're still good. I'm the son of a master locksmith, so this should be super simple, barely an inconvenience. We're going to rebuild the original key switch. Let's focus on that. Excellent. Okay, so I pulled out the wafer closest to the front here because it was not the right size. But other than that, looks pretty good. Just had to file down one of them. So how this works is we got these that are sticking up. And inside of this piece right here, there's those divots. So as long as the spring tension on these is keeping them up in there, it can't rotate. Now, I did redo this, so it, for the most part, fits with this key just fine. So when I enter the key, you'll see that those go flat, just like that. This top one right here, that's not actually one of the wafers that actuates with the key. That right there is a little spring clip that gives some clicky tension in the actual outside of the cylinder here. And that slides in just like that. Perfect. And ta-da! Well, all you have to do is put that back end on again with some excellent West Systems epoxy, and it should work. No problem. What was there to worry about? What's the difference between an expert and a novice? An expert is prepared for things to go wrong. So, this lock is now completely rebuilt. Works good. Let's go and install it. Well, it's in. Looks good. Okay, on to this piece now. Alright, and I can install this in the back. And we can give the interlock loop a test at this point. Yeah, almost. Okay, should be good. Now, keep in mind that the LED for seeing whether or not this board is working is this blue LED right here. And then power is this LED right here. Can't really see it. I'll move this back a little bit. Alright, so I'm going to turn on the unit, turn off the key switch. Yep, okay. That should be off. And get the button. Plug that in. So, now here's what we have in our loop. We have the power supply going to the key switch, which is right here, going to this output 1/4-inch jack to our emergency stop button. So you can rotate this. Okay, we're good. That's up. Perfect. Let's turn on the laser. Okay. Excellent. So far, so good. This light down here isn't green. Go ahead and turn that off. So that light's still off. When I turn on the key switch, it should turn on, which it does. You still can't really see it there, can you? It's hiding there. Alright. Let me go and actuate that again. Off. You gotta give it a second. It has capacitors. Okay. Turning the key switch. Comes right on. Okay. Excellent. We'll see if there's enough power to throw the relays. Okay. Looks good. Now time to hit the stop button. Yeah. Cool. Now because this laser is so powerful, and we're talking an equivalent energy of 60,000 suns, I really want to make sure that dust can't get inside of the unit. That's because if the dust or dirt gets on the surface of the optics, it can cause hot spots, and that destroys the optics pretty quick. So to help with that, I've made these 4 rails. You see one of these right here attached to this side. I've already made the one for the back and the one for the front as well. And this is what they look like. Now these rails sit just like this. And what I'll do is lay a fabric ribbon over the top, and that'll give us a nice dust seal when the top of the laser gets put on. Now, the reason why I didn't do the one for this side is because that's going to be a little bit different machining process than the other 3. Let me explain why. So, the first difference is that we have the fans here, so I'm going to need to make a cutout, so that way the rail can slide on. The second difference is that this back section right here, it needs to be cut out a little deeper because this corner is actually longer than the rest of them. And the final thing, we need to put the safety interlock lid switch on. So that's that. And that's going to be mounted along this area here. And that little button's going to stick out of the top. So when the lid gets put on, it'll actuate that switch and tell the laser it's time to go in 45 seconds. So let's go ahead and machine that last rail. Since I already have some of these rails made, it should be a real quick matter of just marking against one as a reference and making a couple of cuts with the jigsaw. Oh, that should go pretty quick. Right, time to wipe it off. Go check it. Alright, so I just got done making this last rail here and installing it. You can see here that there's the safety interlock switch, and when that gets pressed down, it'll complete the circuit going to the delay board. As I mentioned earlier, these rails play a vital role in preventing dust from getting into the laser. We're going to lay fabric on the tops of the rail, but this is not the only place we're going to put that fabric. So you can see on the back of the fan shroud, there's a fabric ribbon right here. Well, I'm going to go ahead and actually put fabric all around this area right here, just to make sure that we have a nice dust seal. So it's not very hard to do. I've got some double-sided sticky tape and some 1-inch wide fabric. So just ribbon, and it really does work well. Alright, now, because on some of these surfaces we don't want fraying edges, what I'm going to do is I'm going to put some black enamel paint along the surface that'll hold those fabrics together, so that way they don't fall apart. And we don't want that inside of the laser either. Alright, wait till that dries and we can put the back cover on. I'm back to put on the back. Well, most of it back actually. So I did a couple of things off camera. Of course, I let the enamel paint dry here so the fabric won't fray. There's also 4 screw holes down here that I drilled and tapped. I'll explain to you what those are in a little bit. And I also did the main cutout on the back panel. So, I'm going to go put this on. And I'm actually going to start with these 4 holes here. So, I'll eventually be putting on a piece of decorative vent material on this section here. And I've got these holes here that of course hold the fan shroud on, but I need something to hold the bottom of that vent section. So these are what those are for. I'm going to actually screw those in because those are the highest tolerance holes. Now to make sure the fan shroud holes line up, I'm not going to be fully installing them, but I still got to check that. Yeah, that's quite nice. That'll work. One of the most vital things for a show laser is, of course, a way to get electricity into it. So here we have what came out of the laser. So there's a couple of things going on in this box. You have the IEC power input here, a fuse, this switch, and on the inside we have a common mode choke, class X capacitor, and class Y capacitors inside. So it turns out that the camera did not quite appreciate being that close to the heat gun. However, the Jigsaw had no problems being close to this, and I got that piece that I need, which is this front section here. The reason why I need this is because it has the copper clips and it'll hold the mains input into the case of the laser really nicely. Take a look at this and you can see that I have my live, neutral, and ground wires soldered onto the input plug, and I use some West Systems epoxy to reinforce it. And those of you who have worked with West Systems will see absolutely no problem with this because it's really good structural stuff and it's a really good insulator. So now I have to solder these wires onto these 2 terminals of the switch. Kind of a shame to solder onto those nice silver plated terminals, but you know, don't exactly have spade connectors right now. So let's do that. Sure, it's in off position so that way I alleviate the tension on these terminals while I solder them. They don't melt out of place. Okay, that's good to install in the back of the laser. Alright, let's go ahead and connect the mains input plug and switch to the wires going into the laser. So first step, heat shrink. Alright, we'll go ahead and pre-tin those terminals on the switch. Solder here. And once again, being careful with how much I heat those terminals up so they don't melt in the switch block. So that looks good. Now here comes the hard part. Everything looks properly connected. Yeah. Now let's go ahead, carefully put that in. I have to find that little corner piece and pocket that in, but yeah. So the last thing I want to do for this particular night is to put the fan grate over here, because sticking your fingers in the fan, not exactly a lot of fun for most people. So I went and I picked this up from my local Menards here, and I think it'll work very well. This material is pretty easy to work with too. So in order to cut this material, what I do is I lay a straight edge alongside a perforated section. I take a box cutter blade or something else that's sharp, and I score along the perforated lines, and I can easily bend and snap it. Gives me very clean edges that way. So what I'm going to do is I'm going to lay this on here. I'm going to find where it lines up with all the holes, kind of get that centered. Let's find a good place. I believe I have one hole spacing off each side. So let's see. Is that the good side? Yeah, that's the good side. Okay. So hole here. Hole here. Down. I say right about there is where I want it to go. Looks pretty good. Yeah. Okay, let's work with that. So I'm going to make a first hole. Say right here. I don't want to drill it. What I'm going to do, take a hole punch. I'm going to punch that hole right out. So, like that. Boom. And there's my nice hole. Just like that. So I'm going to mark the rest of them out. Then I can screw this onto the back of the case. It should look really good. Here's the back side of the laser. So I have the grate installed. That looks really good. Over here I have my mains input. The switch is stone cold, so it's handling the current just fine. Got a little electrical interlock doodad here. This goes out to the emergency shut-off button. The key switch here. All that's left to do is these knobs for the color. I'll get to those later on, but at this point, I think we can go ahead and work on the front install the galvos, and align the optics. And now I can get started on my favorite part, the optical train. So we got our green, blue, and red laser head. And earlier in the video I mentioned that the aperture of the red laser head is actually higher off the surface of the optical breadboard than the green and the blues. So I showed you with two right angle prisms that I can translate the beam where I need it to be. And I made this custom mount, which I put two first surface mirrors in, and you can see that my finger has been translated to the right. So that's exactly what this piece does. Got one mirror here, one mirror here. Laser beam comes in this way, bounces off this, comes out this way. So I'm going to turn on the lasers so that way they're at a pretty low brightness, and I'm going to find the center of each one of the beams, and then I'm going to set this according so that way all the beams are center and the same distance off the surface of the optical breadboard. So red, green, and blue, on we go. So let's take our measurement. I'm going to be using a piece of translucent plastic right here, and all I'm going to do is make a mark on it, seeing if the height is the same. So we'll put that there. Get burned by the blue beam. Alright, go over here, see if that's the same. It is the same. Very good. Okay, so we need the red output that far off of the optical breadboard. That'll be our center point. So I'll put that optic into position. Now we have our output coming out of that, and we have to set the height. Oh, let's see where that is. Needs to go up just a little higher. So see, about right there is perfect in height. And then we can make our fine adjustments by rotating this whole piece there. Perfect. Alright, so now what I need to do is I need to figure out where the mounts, little kinematic assemblies, need to be positioned, and I need to figure out how I'm going to set the dichros for mixing in the different colors. So for now, what I'm going to do is I'm going to take this mirror right here. I'm going to replace this. The mirror's not in the best condition, but I'm going to take that optic, I'm going to move it over, and I'm going to reflect the green this way to merge with the red, and then that'll give me a good idea of where the other two optics need to go. And I think what I'm going to do is I'm going to try to have the beam follow this row of holes here. So turn up the green a little bit more. Alright, so now we're lasing. I'm going to put a beam block by the galvo amplifier because I don't necessarily want that to burst into fire. So go ahead and grab this. This will be a good beam stuff, I suppose. Probably not. We'll do our best. Okay, and then I'm going to move this out of the way. Back like that. And then I'm going to shoot the green over this way. So my goal, line this in here. I need a stick in the hole. That'll work. Alright. Now we'll stick that right in the hole. So it's about here. I'll shoot the green that way. Alright, I'm going to set the height. And remember, our center should always be on this dot right here. So that's good. That's good. Alright. Go ahead and finish tightening down this mount. These are not friendly mounts to use. I mean, are you kidding me? Why are you loose again? This right here is smart stupid. I should never have to take the mount out to adjust the mount. Never. I should never have to do that. Now we need to figure out where the two are going to meet as far as the green and the blue. So let me show you that. You see here, that's where the green is. That's where the blue is. At one point when I move this card, you're going to see that they meet. So right there is where our optic is going to need to be. So now we got to figure out where that optic is going to sit. So right there. Now we have to position the optical mount in an area where we can put that acrylic filter on and have it situated so that way this mount doesn't obstruct this beam or the blue beam. So see if we can figure out a good position for that. And it needs to be at a 45-degree angle. Our point that we need to get to is here. And here's what we have. So we take this. Can we get that to be in the correct area? Yes, we can. Okay, cool. Yeah, that'll work very nicely. Okay, so what I'm going to do then, I'm going to take the mirror off this mount. We're going to put the first acrylic filter on there and then put this into position, which will join the green and blue beams together. Some optics have been mounted. So let's take a look at this first mount right here. And by the way, these are called kinematic mounts, and they allow you to adjust the beam position with these two knobs on the back. Really handy, and you'll find them in a lot of optical systems. So we got the green laser that comes in this way, and then it hits the first surface mirror that's mounted on the front of this kinematic mount. Put a new mirror on there, and that deflects the beam off at a 90-degree angle. And I'm using these threaded holes in the bottom of the optical breadboard just as an alignment kind of positioning to help. So let's take a look at that. There's the green beam right there. Go ahead and adjust the exposure on the camera. So that's the green beam there. And you can see it's deflected off at 90 degrees. And then we have another kinematic mount right here. And attached to the bottom hanging off is the acrylic filter, the mirror. And what that does is it takes the green laser light that comes this way. The green laser light passes through that optic. We got the blue laser light over here, which comes towards this way and hits the surface of the optic, the acrylic filter, and bounces off this way. So on one side of that optic, green, over here, blue, and since green goes through and blue reflects, that means that they're both going to meet up on this side, so we'll get a nice teal off that end, just like that. Now of course we need to combine the blue and the green with the red, and that's done through another optical mount. So that optic has been installed, and that's right there. And you can see the green and the blue hit the back of the optic. Now those get carried through, just like the green went through the first acrylic filter. But the red gets reflected off. So the red comes out of the height adjuster towards the optical mount and then gets reflected off. So you can't really see it. Time to move the camera. Alright. So got the red here. And the red reflects off this optic. So that means that the red gets merged with the green and the blue. And on this side, we have all three of the colors giving us a nice white. And we want to make sure that they're all aligned and going through the center of each other. Of course, with the red being the biggest, that's going to be on the outside edges. Would you just contrast properly? Alright, that should have fixed it. Alright, so I'm going to zoom out. Now, all of this optical alignment, as I said, is what's considered to be in the near field, and it's called the near field because it's in the laser itself and it's close to the output. But we also want to make sure that it agrees on the far field, which is the area that's far away from the laser. As I move the card back and forth, you can see that the beams all stay together. Alright, I'm going to zoom out a little bit more if I can. So now we have a potential for a lot of laser power. 65 watts, which is a lot of power. Let's go ahead and play around with that a little bit because we can. And I would say, don't do this at home. But if you have 65 watts of laser power, nobody's going to tell you what not to do. That's kind of my thinking on it. Cardboard test. I'm going to turn up the laser to its maximum brightness. We'll see just how much power is in there. So, up in program. There we go. And then I'm going to turn up the back knobs. Alright. So now we have a 65 watt beam coming out of that unit. That's a very spicy beam. We have very room temperature cardboard. Instant fire. I don't want to contaminate the optics too much. So let's do something else fun. I'm going to turn off the lights in the room real quick. I'll turn off that. Turn off that. Alright. And finally, that light. So essentially, it's a dark room. All the light that's generated in the room will be from the laser itself. Enable laser. Alright. Now that looks bright. It's hitting a beam dump right now, which is essentially a very dark object that absorbs light. So, what happens if we diffuse the laser beam, say by use of this piece of metal? How much light will we get? 65 watts of light. So let's go ahead and do that. I'm going to stick this up. I'm going to reflect the laser light up towards the ceiling. It lights up the whole room. That's a lot of laser power. Alright, so the aluminum block is going to be for the galvos. Now, also just to make sure I don't fry the galvo amplifier, I have here another piece of aluminum dark heatsink material just in case the beam gets turned on. I don't shoot the galvanometer amplifier. But that block is going to sit right here. And the galvos, which are GT30 Pros, so these are Dragon Tiger galvos. They're a mid to upper tier brand. Got the big mirrors on there too. We got a big beam. So now, we got to figure out exactly where the galvos need to be positioned and see what the height is. The first mirror that the laser is going to hit is the X mirror, which steers the beam back and forth like this, which is this mirror right here. And they actually make that smaller, less mass on the mirror. They don't need to have it stick out that far. Also makes scanning a little wider, a little easier on the galvos. But anyway, so we're going to put that in there. We're going to turn down the laser power in the back just to make sure that we don't cook anything. Because once again, we're just doing positioning at this point. Turn down the laser power on the program and enable laser. Now, essentially at this point, all we need to do is line up the red because the red's the biggest one and that's the one we're going to worry about the most. So, zooming on the galvos right here. I'm going to move the camera get a better view on that. Okay. Perfect. So we want to make sure that all of the laser beams hit this right here and none of it leaks off. And this will determine how high we need to machine the aluminum block so that way everything's perfect. So we're going to turn on the laser and we're going to see where the red lines up on that X mirror. Just like that. So very dim. We're going to see where the positioning needs to be now. Alright. Set it about 45 degrees. And if you see, the galvos are up just a little too high because we have some cast off on the bottom. So it looks like we're going to need to, say, take about 1.5 millimeters of thickness off the aluminum block, just so the galvos are at the right height. The other thing we're going to need to do is we're going to need to line it up with the output of the laser window. There's the aperture output window right there. Flying camera action away. Stick the phone in the laser beam. In the laser beam. Alright, so that's where the galvos line up now. Take a look at the output window. We gotta see now how center it is. So that's pretty center right there. And then we gotta drop it down a little lower, but it looks good. So that's where the galvos was set. Now, what I need to do is I need to mark out where I'm gonna put the holes to hold the galvo block in position. Sadly, I got short screws, so I'm gonna need to machine down the sides here so they're shorter. Now I gotta mark out where the galvo block's gonna go. I also need to do the holes so that way the screws can go through. And when I do the cutoff of the sides, it's going to reduce how much of the metal I need to take off on that upper surface. So that'll make things a little easier. So maybe be pretty busy with the saw. And then I got to do the holes on the bottom coming up through the block. And the reason I need to do those holes is because there's 3 screws that need to go up in there. So I need to drill the block out and get it ready for those 3 screws. So all of that needs to be marked out on the aluminum block. And there's some machining I need to do to get that set up. Turns out I had to go with route C as far as making a solution to raise the galvos off the optical breadboard. So I've got my scan block here, and I really wanted to go with a single aluminum piece. Unfortunately, I don't really have a tool that will surface the top of that. So I had to go with another solution. I have 4 different metal thicknesses here to give me the right total thickness. So basically shims, because that really is a touchy height. It's rock solid either way, not going to go anywhere, and it gives me the perfect height. So I want to focus on doing the electrical connections here. I'm going to start by connecting the output of the power supply here, which gives us our positive and negative 24 volt DC rail. So you can see the label over here on the top a little bit. So positive 24 ground, negative 24 has the listing here. So let's go and do that. And we'll double confirm that with the multimeter, that those are proper connections. So here's the galvo wiring harness. Pay attention to this side right now. This is going to be our positive 24 volts, the red, negative 24 volts, which is going to be the white, and our shared common, or in this case it's labeled ground, but that doesn't mean it could be case ground, just DC ground. But we're going to connect these up. The spade terminals provided by the company are too wide. What goofy nonsense is that? Now I can plug this into the galvo amplifier board. Right there. Actually, you know what? Let's do a sanity check first. On. Oh, I have to go get the plug. Xenodiladon, now with 120 volts. So let's go ahead and do a sanity check. Go see if those outputs on that power supply are correct. So between red and black, we should see positive 24 volts. Go ahead and test, which we do. And between black and negative, right, black and white, we should get negative 24 volts, which we do. So that looks good. Okay. Now, I am going to take the cables that go to each galvo. We got two cables, one for the X on the bottom, one for the Y mirror. So go ahead. I'm going to plug in the one for the X. And now we have this wire right here that comes out of the top of the scan block. That's a thermistor, so it determines how warm the galvos are while they're running. And that plugs in onto the board that says thermistor. Which one are you? NTC, because it's an NTC thermistor. Okay, that should be that. So I'm going to turn off the laser at this point. I'm going to plug in the power connector, and we're going to see if these home as they should. What I'm going to do is I'm actually going to move that one out and move that one out very carefully, and so we should be able to see them find the home position when I turn on the laser. So turn it off, wait for everything to power down. Okay, I'm going to plug this in to the galvanometer driver. These are going to be your signal input wires here. I'll move those real quick. Okay. Now I'm going to turn on the laser. We're going to see if both the mirrors home, which they should do almost instantaneously. Which they do. So that's good. Actually, that's a little sideways. That ain't right. Top one's working. Bottom one. That one don't work. That's strange. Don't tell me that's gonna end our fun real quickly. Did I stick that in all the way? Let's see. Maybe not. I've never used these connectors. These are interesting. I've never seen galvos with them. Alright, let's go ahead. Try this again. Y works, does X work? I hope that's the problem. Hey, what do you know? That was. Okay, that cable just wasn't seated all the way. Yep, that looks good. Okay, now, what I'm going to do is I'm going to see exactly what the pinout of these three wires are. So we should get our signal positive, ground, and signal negative. So let's go ahead and test that out. Firstly, we want to identify which one of these is ground. I'm going to turn off the laser unit again. And the simple way to do that is to put the multimeter in diode check mode. And we're going to see what's connected. Makes it beep. So, as I said, I figure it's the sensor wire. So, will we get a beep if we touch that to ground? We sure do. Okay. Let's test the other side. Actually, you know what? Now that we know that one's ground, if we test the two sensors, it beeps. So those are our grounds for signal. Okay. Let's see if it tells us which is positive and which is negative. No. It's going to make us guess. That's nice. Okay, well, we're going to apply the heat shrink on later, I suppose. That's crazy. I can't believe they don't mark that. They don't mark that? How dare you not mark that? Boo. Alright, I'm going to cut these out right here. Okay, so let's think about this. I'm looking at it backwards, so that means that X deflection is going to be that way because it goes that way. So I need to have the gavel flip this way for the positive orientation. So here's what I'm going to do to figure that out. So if I'm looking at the image on the wall, in this case, it'd be like looking towards the video projector. The image will be reversed because I'm looking towards it instead of towards the projection. So I need the gavel to rotate counterclockwise. In this case, I've got these two outside wires like this. I'm going to turn it on. And I still have my multimeter in diode check mode. That puts a potential of about 2.5 volts on my probe tips. So if I touch between these one way, it'll go counterclockwise, and that's the one that I'm looking for, and the other way it'll go clockwise. So let's figure out which is our positive. I'm going to put my probe on that one and my probe on this one. We'll see the deflection with this gavel right here. Oh, that's the Y. Okay, well, that's what we want for the Y. No, we want it to go up in positive value. That's down. That's up. That is the right one. Okay, well, that is Y positive. So I am going to put a knot in that. So we know. Let's go over to the X right here then, do the same thing. And if you're cutting cables and you don't know what is going through them, cut them all one at a time. You won't short things out that way. Okay, so once again, just the two outside ones. Just like that. And once again, we're looking for counterclockwise rotation on there, so let's see what this does. That's clockwise. That's counterclockwise. Okay, so that means that this is going to be our positive for the X signal. I'm going to put a knot in there. Now, the other thing that I need to do is solder that all here. So these are my wires coming from the DB25 port. I have my overall signal ground, so this is pin 25. And then I have pins 1 and 13, which is going to be the black and the red. So the red is pin 1, X positive. Black is pin 13, X negative. Over here I have one that's marked white, it is white, and one that's marked blue. So this is going to be pin 2 for positive Y, and the blue is going to be pin 14. No, pin 13. Yeah, it goes the opposite way. For the negative Y. So yeah, as soon as I hook this up, essentially I should be able to do laser beaming moving things. So let's go ahead and do that. I'm going to shut down the unit. And we'll get some soldering done. You can look up the ILDA pinout too. It's easy to find online. If you ever need to connect your own galvo set, it's actually really simple to do for the most part. That looks mostly out of the way. Mostly. Okay. So I'm going to turn on the laptop and get the laser running. So give me a minute and we'll come right back. And now finally, the moment that everyone's been waiting for. Will this whole thing work or will it not? So I should have full control over all the laser heads and the 2 galvanometer mirrors. So we should get a test image if we're lucky, and if we don't, well, you know, we'll deal with that bridge when we get there. But let's go ahead and see. I have Pangolin Quick Show running, and I'm ready to turn on a pattern, so I'll go ahead and check that over real quick. Make sure all the knobs in the back are turned down for the time being. Test pattern set at 20% brightness. Yeah, let's try this, see if it works. Turn up the brightness. Hey, that looks promising. Oh, that's perfect. That is superb. Right. I think I have to turn it down really low so you can see, but it looks good. So let's take a look at the test image. That looks proper. Yeah, I can read that. This is top. That's pretty nice and square too. Can't complain about that. I say that's good, right? Nice, very nice. Well, time to see what we can do about the shutter and the output window and a couple of other things, but functionally, it's a working show laser. Let's discuss another safety mandate. So here in the US, a lot of laser products are required to have a mechanical shutter, which will terminate the beam and prevent it from leaving the actual product in case of a malfunction, if the interlocks are no longer properly engaged, or if the emergency button has been pressed. And show lasers are no different, especially with this kind of wattage. So the laser came with this rotary actuator right here, which isn't the best, and I've tried to make it work as best as I can. And I have this little mechanical arm that comes up, and I have my little beam stopping flag right here. So in theory, it should be suitable, right? Well, the original end of that little flag, which is right here, was made out of steel. And if you take a look at it, you can actually see that it started to melt the steel plate, which was no good. So I tried to replace it with a little piece of titanium hanging off the end, and is that good enough to stop 65 watts? Well, what I'm going to do is I'm going to turn down the laser. I'm going to remove this because this is holding up that little beam stop, and you can see that it's right here. It's interrupting the beams. What happens to this titanium flag when it gets hit with 65 watts? Let's find out. Alright, so I'm going to disable the laser. I'm going to turn up the brightness to 100%, and we're going to whack that little thing. Ready? Yeah, it's not good enough. That's the problem. So, well, big animals require big cages. This is no different. We're going to need to make a serious shutter for this thing. And this ain't making it either. So we're going to use a much bigger solution. It comes with free screws. What do you know? Oh, so much for that shit. Saw blades. Time for you. Time for me. Let's get some machining done. These don't say metal anywhere, but I'm sure that between 10 of them, they'll work just fine for the job that I need to do. Also, looking at the available space inside of the laser, I realized that on this section, I might want to keep more of the material to put counterbalancing weights or whatnot on it. There's actually not that much room going back, so the more metal I have above here, the better it is for me in that case. So what I'm going to do, alright, let's improperly use the saw blade. Alright, well, I'm going to have to clean that up with a file. So far, so good. After a little bit of work with the metal file, the shutter flag is looking pretty respectable. So there's one other thing I want to do. You'll notice that on this section, I have some vertical and some horizontal lines. So what I'm going to do is I'm going to saw down those lines, which will leave me with these little tabs sticking out. And I'm going to turn those tabs by 90 degrees, and that'll hopefully optimize the amount of heat that this section can dissipate. That should do. The mechanical shredder is now in its final form. Let's see what we have here. So here's the actual beam stopping end, and you'll notice that I have a bunch of little heat sink fins on there, which will help get rid of the heat from the laser beam. Now, this is a somewhat reflective material, so we only have to deal with what's absorbed. The rest of it gets diffused safely inside of the laser case where there's no eyeballs, and we don't want something that's mirrored because that can shoot all the energy back into the laser and damage those laser diodes. The nice little cutout here, so that way the red laser beam can make it through and hit the dichroic filter mirror that it needs to. And I reduced the mass on this arm by cutting out all these little holes here and drilling them out. So that means less mass for the motor to move and faster response time. Now I also have two springs, so one spring here, one spring here. That gives me a nice little center point that the arm returns to. Now, since this is a fairly large motor, it takes quite a lot of current when it's stalled, which isn't necessarily a problem in this application. So our real numbers are, we got about 1 volt in and about 4.5 amps going into it, so about 5 watts of heat generated, which in a package this size is next to nothing. However, the 5 volt power supply that I have installed inside of the laser will only adjust down to 4.5 volts, which means that I gotta drop about 4.5 amps at about 3.5 volts, giving me roughly about, let's say 13 to 15-ish watts of energy that I need to get rid of. So I got two 2.2 ohm resistors here. They get rather toasty, but that's okay. We have a lot of cooling potential inside of the laser. I would use a little DC to DC converter, a little buck converter to step down the voltage, but it's a very noisy load when you're switching it on and off, so I don't want that failing. Harder to kill than a DC to DC converter. I've got a diode here that's in reverse, which is my flyback clamping voltage diode. Little capacitor here to snub out some of the back feed noise as well. Now let's go ahead and turn it on. Raise the gates. Ta-da! Look, it just needs to be opaque and remain opaque in case of emergency. It's not that exciting, but yeah, it should work. There's one more thing that needs to be done. So these are the original color knobs that were on the laser for adjusting the color brightness, those potentiometers. Yeah, they got pretty beat up, so we're gonna make nice new ones. Now, I could only find plastic replacements, and I wanted something a little nicer for this project, so I picked up these. They're guitar knobs, Cash brand. They're pretty good, actually. So what I did is I put them on the lathe, and I cut out this portion here, and now I have a pocket of which I can put some paint. Right, that looks pretty good. And that'll go well with these. So I'm gonna probably put a layer of epoxy over the top of all these. I noticed that this one isn't all that glossy. Kind of has a matte finish to it, so yeah, those look nice. Well, it has been a big project, but now it is a done project. So real quickly, before I go ahead and do a final cleaning and dusting and then button it all up, let's quickly take a look and see what's inside. So here are those galvanometers, the laser scanners. These are made by Dragon Tiger. These are DT30 Pros, working pretty well with those big mirrors on there. Custom shutter assembly that I put together. Now I'm not going to go and do a hot beam at full power on that flag. Let's face it, that will remain opaque for as long as it needs to. A nice design with those little heat sinking fins and stuff on there. There's a little beam stop right there, a little beam dump that I made because there's a little bit of cast off waste beam coming off that optic, so that's no longer a problem. Over here on the shutter mechanism, I have these end stop springs that I put on there, so it keeps the shutter where it needs to be. They custom mount an optical assembly for the red. That went together really well. Yeah. The blue and the green laser heads. My little sensor for the temperature between those two. The dichroic mounts for the optic. So dichroic filter on this one, first surface mirror on this one. The plate with all the laser drivers on it. That looks good. My little mess of analog electronics for the fan speed control and the safety interlocks and stuff. That looks good. Fan shroud. Power supply for the shutter mechanism, shutter motor. Now over here's that fan power supply. So everything's working. Everything's doing its job real well. Yeah. Turned out really good. Really good. So, you know what? Before I button this up fully, we'll go ahead and do one ubiquitous, needs to happen, beam shot with fog. Because we have to. It's out low power, by the way, so not like it's going to be a big problem. We're not going to have any burn-in. A part of me doesn't want to be on this side of the laser. I've already been burned by this thing. It's no fun. Well, let's go ahead and do a final cleaning and put it together. Man, that's gorgeous. That is a good looking laser. Great use of 4 cubic feet. Very nice. Over to the side. Take a look at the back. Very nice looking. It's a fully resurrected curtain burnosaurus. This laser is absolutely bonkers. Do I wish to turn on the laser? Yes. Well, that's about it for this video. As always, stay tuned for more. Turns out they actually do go pew.